laser pen. Okay, so our duty today is to derive the equations for exergy. How do we? So suppose now this is a system. It is at a high pressure and temperature. Pressure higher than P naught. T is higher than T naught. This work done and this Q in or out. So this system is not equilibrium with surrounding, and it can having velocity, it can having height. So this is we know now it has exergy. So how do we calculate this exergy? We need to develop a formula to calculate the exergy of the system. So at this state, it has a potential to give us work. It has pressure higher than P naught, then this can move. It have a temperature higher than T naught. It can have a velocity. It can have a height. Then it has exergy. How do we evaluate in numbers how much this work can give us work? What's the maximum work I can get from this system? So this is what we're going to do today. I don't want the derivation is a little bit complicated. I don't want you to worry about that. Just understand the features of that. I'm not going to ask you to derive the equation, but what's most important, once you derive the equation, then how can we use this equation? So now I'm considering this system here. I'm driving how much exergy. So this is what we're looking for. What is the exergy of this system? Of course, it will be function of the pressure. If the pressure that have high exergy, if the temperature is high, it is high temperature. If there is a heat added, then there will be higher exergy. And if depends on the velocity is high, it have exergy. So exergy definitely will be function of all of these parameters. Okay, so this is a system here. This system giving work, delta W, and then it has a Q here. This can be positive or negative. We can take this Q out and pass it to a heat engine, and then we get extra work here. We call it W heat engine. So we're going to look at for the maximum work I can get here, this both of this two here, and this will be the amount of exergy for the system. Because the exergy system is that let this expand all the way to P naught and T naught, and then calculate the maximum work. So this is the maximum work I can get. And of course, we're going to treat this system as reversible to get the maximum work. This is what we agreed upon. Okay, so now let us consider this here. So for this system, we apply the energy equation. So 0 minus W delta Q minus delta work is equal to du. So this is the energy equation applied to this system. According to the work here, W will be equal to W useful plus P naught delta V. As you mentioned, there is an expansion of this at P naught. We cannot get it back, so this is unuseful work. So now we calculate first here the WP useful, which is the maximum work I can get from that. Okay. Then we have to consider the reversibility of the system. This Q here, we are going to take it to a heat engine. And for a heat engine, we apply delta work is equal to eta multiplied by delta Q, which is 1 minus T naught over T multiplied by delta Q. And accordingly, we can calculate here delta work of the heat engine. And then in the next page here, I'm going to add both together here. The delta work total useful is the two amount of work for the heat engine and the work for the useful for the expansion. So I have work here expansion, and there's a work here from the heat engine. We add this together here, and then this is the work we get. And accordingly, this work, we will call it the exergy. And accordingly, if I consider this here, then we can say here, this X is the exergy of the system. It will be equal to U minus U naught, the internal energy minus U naught until it reaches, we take this internal energy until it is in equilibrium with the surrounding. U naught here is the internal energy at P naught and T naught. U here is the internal energy at the temperature and pressure of the system. Okay, so now this is the difference here of the expansion of the system from P and T to P naught and T naught. Also, there is an expansion against the atmosphere, which is P naught V minus V naught. And this term comes here from the analysis, T naught, S minus S naught, and then kinetic energy and potential energy. If you take this per unit mass, which we used to have, so I say the exergy per kilogram, this will be U minus U naught, P naught V minus V naught, and this to 3 times there. Let me explain this. What is that? And how do you calculate this? This is the most important thing here. Also, you do not have to memorize this equation. It will be given in the formula sheet. But now you want to understand what are these terms and how to evaluate. So be with me now. And if you have any question, please stop me and ask. I'm saying again, this is the equation. You should understand this equation and how to apply it, how to get the terms here. I'm going to take numerical example later on. But now I want to consider what is phi here. Phi may be different in the book. They call it sometimes E as exergy. So phi here is the exergy of a system. System means there's no mass in and out, and therefore here this is in the previous system that we have. Okay, let me try to get this here. Let me try to get this in this page. Okay. Okay, now I have this system here. What's phi here? As you mentioned, this system, because it has pressure and temperature higher than P naught, and kinetic energy and potential energy, then it has exergy. So what's the exergy in that? This is phi. Phi is the exergy of this system per kilogram. Okay, so this exergy in kilojoule per kilogram. I understand. I'll ask you after each term. Phi is understood now. What's that? Shabab.
Yes, doctor.
Okay, so it is the exergy per kilogram. So every kilogram of that will have this exergy. Now what's U here? U is the internal energy of this system at this state, at P and T, before it moves. So this is the original one, before we try to get work from that. How do you get this here? From the table. So you know the pressure and temperature, you go to the table and you get U. So this is the internal energy of this system at state 1, which is P and T. Then what's U naught? U naught is the state, is the internal energy of this system when it goes to P naught and T naught. So you go to the table again, but this time at P naught and T naught. And then at P naught, which is 100 kilopascal, and T naught, which is 25 degrees centigrade. So now you get U minus U naught. So this is here is the exergy. How to calculate here is the physical meaning of that here is that we let this system expand to P naught and T naught and see how much exergy, how much work we get. So this is this part of it here. So this U minus U naught. Shabab, any question about understanding what's U and what's U naught and how to calculate them from the tables? Questions? Are you sleeping or what?
Clear.
Okay, understood?
Yes, yes.
Then,
Yes.
very good, thank you. Then plus P naught is the atmospheric pressure, which is always 100 kilopascal. V minus V naught. What is V? V is the original volume here at P and T. So if this is an ideal gas, you say PV equals RT, and then you get the specific volume. So this is the specific volume at the initial state that we are looking for. Then it will expand to V naught. So now when at P naught and T naught, we'll get V naught. So if this is an ideal gas, we'll also go and calculate P naught, V naught equal RT naught, so we can get V naught. If it is a steam, then we'll go at P naught and T naught and calculate V naught. Okay, let me ask again, is that clear, this term?
Yes.
And also you can calculate from the
Yes.
table. Okay. Then minus T naught. T
Yes.
naught is 298, which is the temperature of the atmosphere. Remember, this has to be in Kelvin. Then S minus S naught. S is the entropy at P and T. So you go to the table again, get S at P and T. Then S naught is the state here at P naught and T naught. So you go to the table and calculate S naught, but at this P naught and T naught. Then plus V squared So this is V squared. And of course, we do not subtract here because it should be 0. It goes to 0. So this is the velocity at the initial state minus the velocity at the dead state, which is 0. So this will be V squared plus GZ, which is the height of this system. So these are the elements here. We calculate these elements, and this will be phi, which is the exergy at this system. And normally we can call this here, this term is here as E minus E naught, but this is not important here. So I want you to stick with that, and you'll find it in the formula sheet. I'm sure of that, but if you do not find it, you don't have to memorize it. Also, do not have to derive it. But what's important here is to understand this and how to calculate this from the table. Let me take the attendance now, how I have to go out. Okay. Let me go out, take attendance, and come back, please. Okay, I think I need this one. Okay, it's done. So let me share again. Okay, here we are back again. So this is the equation for, remember, this is for a system. You see, do not see any mass flow in or mass flow out. So this is for the system. Now, if we have motion from one state to another, okay? So this is here, phi here, as we mentioned, presents here the exergy of this at a certain state. Now suppose that this expands to another state, but not to the dead state. So now we say here, delta phi is phi 2 minus phi 1, which is exergy at state 2 minus exergy at state 2, 1. And therefore we say here that this will be u2 minus u1. Okay, it's not given here. So we consider phi 2 minus phi 1 as u2 minus u1. So this will be u2 minus u1, p naught v2 minus v1, t naught s2 minus s1, v2 square minus v1 square, and gz2 minus z1. So this will be the change in the exergy of the system. Now we'll go to exergy of a flow. If there is a flow, now control volume. The difference here is that W flow will be equal to PV minus P naught V, because we add delta P W flow is equal to PV, and then we have to add this to the work. So now we consider if we add this here, we will come with another equation. So if I consider the U minus U naught and add here delta P delta V delta P, then we get another equation here. So for a system that's flowing, this will be the case here. This will be the equation here. If there is a flow that has a mass, so say H minus H naught, so instead of U minus U naught, it will be H. We used to have this in the first one as well. U will change to H, so H minus H naught minus T naught S minus S naught plus V squared over 2 plus GZ. So this is the case here that these are the two equations that I want you to memorize, psi and phi. If I'm looking for delta psi, then in this case here, delta psi will be psi 2 minus psi 1. This will be equal to H2 minus H1 minus T naught S2 minus S1, and this here. Now let me ask you one question. Psi here is the exergy at state 2, right? Psi 1 is the exergy at state 1. Delta psi, what does it mean from the terms that we have earlier? The difference between exergy 1 and exergy 2. What did you call it? Huh? I cannot hear you.
Reversible.
Very good, very good. Thank you. Can I know your name?
Faisal.
Okay, Faisal. It seems that you are doing a lot of good work. Okay, so please mention also your name first. I think you say you are the one who sent the calculation of U naught, H naught, and so on.
Yes.
Okay, because I saw a different name there. You do not call yourself Faisal in the WhatsApp. Okay, thank you, Faisal, for that, and I think it should be helpful to also. So this is the reversible work, so we can calculate. So now we can calculate the exergy. we can calculate the exergy at another state, we can calculate the reversible work, and also this reversible work will be equal to what? Will be equal to W actual plus irreversibility. So reversible work we can calculate from thermodynamics 2 here, or as previously we calculate from thermodynamics 1. Okay, so now so far what I want to concentrate on, what is the value, how do you calculate exergy, how to calculate exergy difference for either a flow or a system. There is no memorization, only we want to understand this and how to apply it, and we'll have examples. All right, so now this is what I'm going to do here, and of course the destruction, which is the reversibility, will be equal to T naught S generated, and then let me go to this is I just want to derive a general equation now for a system or a control point. I just going back to with you, how did we derive the energy equation? So the mass conservation energy equation, so on. When we had a mass balance, mass rate balance, then we said that the rise in mass inside here will be equal to M inlet minus M exit, and this is how to derive the mass conservation. We will follow the same in driving the energy and driving what we call exergy balance. We want to calculate an equation similar to that, and we call it exergy balance. We want to relate the rise here in terms of the in and out. We have done this also with the energy, and with the energy we took this system here, this control volume, and then we set here the rate of increase inside the control volume, which is dE by dt, will be equal to Qn minus Q minus W out. So this is the energy minus the energy out without a mass, then plus the total energy in accompanying the mass minus the total energy exit accompanying the mass exit. So this is how did we derive the equation. So we had two very important equations here from thermodynamics 1. One is the conservation of mass, and of course, if this is a steady state, this term will be 0. So Mi will be equal to Me. If this is a control volume, those two terms here will be 0. Same here for the energy. If this is a steady state, and this will be most of our applications, this will be 0, and this will be the equation 0 equal to that for a steady state. If this is a system, those two big terms here, Mi and Me, will be equal to 0, and then dE by dt will be equal to Q minus W. So we have these equations, and then how to apply them to a system or a control volume. Now I want to go now to exergy rate balance in the same manner that we have here. Okay, and as I mentioned there before, that this is the view of energy and this is the view of exergy. We translate every term of this here, Q, when it comes at exergy, it will be multiplied by 1 minus L over TH. Enthalpy will be changed to X that we called, which is H minus H naught, and so on. So this is what we are going to do. So now we apply, this is the system, the system here, and this is the energy balance. Okay, so this is the energy conservation. We apply the same here. Now Q in the energy will be translated as what? Will be replaced by this term, right?
Yes.
Okay, so now I'm looking at this. This is the energy equation, and then if I have Qn, the exergy in Qn, it will be into this term, 1 minus T naught over T. And then I have the work here, so the work is work. The work does not change. But still I have a change in the volume. When there's an expansion in the volume, there is a work loss here as P naught delta V. And then this is the energy equation. The energy equation will be replaced now by psi n. What's psi n? Is the exergy. So this is the energy accompanying to the mass. Now we replace this term here by psi exergy, which we have already calculated just some minutes ago. Then minus energy here will be changed to psi to exergy x. And then we add another term here. What is this term? This is the irreversibility, because this is the destruction of the exergy. And the energy do not have any destruction, because change transforms, there is a transformation of energy. But in the exergy, we have x dot here, destruction or the irreversibility. And according to that here, this is a rise in energy of the system. Here, dx will present the rise in the exergy of the system. I will repeat this again here. We are considering sigma exergy n, which is this term, plus this term, minus exergy exit, which is this term and this term, but we add here minus the destruction, because the exergy has destruction. This will be equal to the rise in the exergy of the control. Don't blame the lecture here if you don't understand this, because first of all, do you understand this or not? This is thermodynamics one. If you don't understand this, definitely you will not be understanding this one. But if you understand the energy, then it is easy to do that. So the energy says that the rise in energy of the control volume will be equal to sigma n, which is Q, plus the mass multiplied by energy n, minus energy exit, which is W, minus the mass multiplied by this term. So this is the energy conservation. We have also what we want to derive now, the exergy, but we don't call it conservation. Why? Because it is not conserved, because there is a destruction here. But we will do the same here. Sigma energy n accompanied with Q will be translated as that. Then sigma energy n, sigma exergy n will be the mass multiplied. Instead of energy, we put the exergy term here. What's psi? We have the expression in the previous slide for that. Then minus, instead of energy out, which is this term and this term, we have exergy out, which W will be presented by this term, and then this will be presented by this term. Then we add irreversibility here, and this will be equal to the rise in exergy. Psi here, every psi is presented by this amount here. So you consider sigma mass n, psi n will be equal, so every psi here will be replaced by that. If you compare this with that, all what we have done is removed the enthalpy or internal energy here and replace it by these two terms. So also, so this is, I want you to understand this equation. You don't have to know, so it's available in the formula sheet. And every psi here you substitute in that and then apply it to a system or a control volume. So let us see how it happens with the control volume now. If this control volume, if it is a steady state, and all the time in this course will deal with a steady state, so this will be zero. So you know now how to calculate this. You know how to, this will be given, Q will be given, the work either given or you calculate integral of PDV, and then dV by control, this will be, if it is a steady state, this will be zero. So this term will be zero, and this term will be zero. Then you calculate this here from these terms. And the exergy exit, the destruction, you can calculate it from T naught is generated as we have done in thermodynamics 1. If this is a system, what happens here? This will be there. This will be there, both of them. But this will be zero. There is no mass inlet. This will be zero. There is no mass exit. So those two terms will be deleted. All right, Shabab? Shall we go to example?
Yes.
You need to review this lecture.
Yes.
You need to review the online course. You have to do some work from your side. It is like practicing driving. If you want to have the test for driving the car, you cannot go there without study. You will fail there. But if you take the car and drive it, hit it here and there, you will learn and you will succeed in the test. So this is exactly, it needs practice. Okay. So now this is the equation here. We derived, I'm summarizing this again. I'm summarizing this all again here. So this is the general equation for the exergy, and then this is our set 1, set 2. Every psi here you will define from this term. And now, if you are talking about a system, you need to calculate exergy at state 2 and 1. And for this term here, for a system, this will be phi. You can calculate it from this term. So this is the picture I want you to learn and practice this one. How do you calculate, how do you apply the exergy balance? Remember, we call it balance. Why? Because it's not conserved. Now let us go here and take an example. I hope I can take example or two today. This is an example here. Let us read the example carefully. So let us understand the question. a balloon, this is the balloon here, filled with oxygen. So we have oxygen here, and it's giving us 280 Kelvin and 1 bar. So we're given P and T. Okay. Then it moves with a velocity of 15 meters. So we're giving the velocity at an elevation of 0.5, each relative to the Earth's surface, where T naught is giving us the dead state here, T naught and P naught. So this here, because it has at certain conditions here, temperature and pressure, velocity and Z, it has some exergy. We want to calculate the exergy. And we are given here the state T naught and P naught. Normally we will give you T naught and P naught, but in an exam, if I forget to give you T naught and P naught, shall you raise your hand, ask Habib, what's P naught and T naught? Do you do that?
No, assume B naught is equal to 1 bar
Yes.
and T naught 24.
Very good, very good. So you can assume it yourself, whatever, but normally is a 300 Kelvin and around 25 degrees centigrade, 298, and the pressure will be 1 bar. So if I don't give you that, it is the atmospheric condition that we all live in that. Do you understand the question? The question has a temperature, balloon, temperature and pressure, velocity, and Z. And the question here, you determine the specific exergy. We need to see how much exergy this balloon has at this state. Okay. Remember that the exergy is at a certain state. Okay, so this is at a certain state. It has nothing to do with the process itself. It is at this state. It has certain amount of exergy. As I told you before, you are going to the shop. You have 100 Saudi Riyal. Out of the shop, you have 130 Saudi Riyal. 30 Saudi Riyal does not have to do anything with what you have done. It is what do you have in your pocket at this stage. So this is the state here. With these conditions, it has exergy. We need to calculate what is this exergy. The question is clear? Shabab?
Yes.
Yes.
Very good. Let us go now. So we have this equation. It is given in your formula sheet. All right. So now you have it's calling it E here. This is the book that you should have now. This is the exergy. Instead of calling it phi, I'm call it here E. It doesn't matter the symbols there. But this is the same equation as we have before. So we want to calculate all of these terms here, add them together. This will give you the exergy of this. What does this exergy mean? Exergy means here that, let me go back here. What does physical meaning of this exergy? It means that this balloon, if it is let to expand to the dead state, how much work it can give. That's what is the meaning of this exergy. So when we calculate the exergy here, this exergy is equivalent to the maximum work that this balloon can do until it reaches the dead state, which is T naught, P naught, V equals 0, Z equals 0. Okay, so now we go to, this is the term here. This is the term here. How do we calculate this term? U minus U naught. We'll go to the tables of ideal gas and we calculate U. Of course, U will be defined as the temperature, which is 280, and U naught will be defined as the temperature, which is T naught. So we'll go to get this from the table, nothing more than that. And this is, we will find the table kilojoule per kilomole, and then we need this per kilogram. We normally like to have this per kilogram. So we divide by the molecular weight of oxygen, and we get this here. Can anyone explain why this term is negative here?
Yes,
Yes, please go ahead.
because the first state is the temperature is less than
The temperature is this, yes. Very good. Thank you much. Always give your name. Whose name?
Faisal thing.
Okay, Faisal, huh? Are you the only one attending or what? Ah, okay. So now, because here 280 is less, so this term will be negative here. Okay, because it is less than the atmosphere. So now we go to the second term. Second term is P naught. We have P naught is 100 kilopascal, and V minus V naught. How do you calculate V and V naught? V will calculate it at the state which is 280 and 1 bar, and V naught will calculate it at RT naught over P naught, and therefore we can get this term also at negative here because this has a certain amount here. Okay, so now we have this is the second term. We'll go to the third term, T naught S minus S naught. So now we'll go to T naught is given, S we get this from the table at state one, minus S naught as T2. So we can put it in this term here, S minus S naught minus R ln P over P naught, and then we calculate this, we get the value for this here. Then we go to V square. V square will be calculated as the velocity plus GZ is calculating both two terms here, plus GZ. Remember that this in meter square per second square, and therefore we have to divide by 1,000 here. So this V squared over 2 will give me here this amount as this one here. Then we add all of this together, and then we calculate, adding all of these terms together here, we calculate the exergy at this point. So at the end here, this has this term here, U minus U naught, V minus V naught multiplied by P naught, V squared, and no, T naught S2 S minus S naught, and then we have the kinetic and potential energy, and this will give me that. Some students may forget this one here, okay? And this will be a big mistake. Remember here, if you forget that, because why we have to divide by 1,000? Because the units here is units, so this will give me joule per kilogram. But this I'm talking about kilojoule. For unfortunately, the tables will give me always kilojoule. So I make sure that this is in kilojoule here. So if you find this too much, then this means that you forgot to divide by 1,000. All right. So this is one case here, and this is for a system. I like to go to another example. I'll start it. I think I'll be able to finish it or not. Then we can continue next time. So any question in the previous example? Is it easy to calculate? What you should do at home today, you go to this statement and resolve this example again. All right? This is what you need to do today. So we used to have, when I was in your age, I used to have notebook. One side I leave it for the instructor, and then I write the notes while I'm talking. You can do this also while I'm talking. You can have some notes, and the other page is yours. The other page is yours that you go and so I solve this example here. Then you go back home and solve this example. Close the solution and then us. And then you can, when you stop at any point, then you can check the solution and then learn yourself there. So you are not nervous at home, you are relaxing, and you can have look at the solution at part time and then continue to solve the problem. So make practice on that. So this is what you should do. When you come at the end of the semester, you find the page of the student here and your note is full, then you have done a good work. If it is empty, then you have done sloppy work. Okay, now let us go to another example here. It says, let us understand that it says steam. So now we have steam now. So we cannot use the ideal gas table. Steam enters an adiabatic turbine. Adiabatic means that there's no heat transfer here. So steam enters, we are given the pressure and temperature, and also are given the velocity, and is not giving us Z, so we can neglect the kinetic, the potential here. It's giving us also at the exit, giving us the velocity, pressure, and temperature. And he says that he's giving us 5 megawatt here. Is it clear the data we have? I have a steam turbine, we have inlet condition, pressure, and temperature. Accordingly, once we have pressure and temperature, then the state 1, we can give the enthalpy, entropy, all the properties at this stage, because we have two independent properties. At the exit here, it has the pressure and temperature, so also we can tell here what are the properties. We can get all the properties here from the table. It's giving us the velocity at inlet and the velocity at exit. And he's giving us the work here. Why is giving us the work? If I have this data here, only this data here, what can I calculate the work or not? Without this W 5 megawatt. If I have this here, can I calculate the work?
No.
I can calculate the work per kilogram, right?
Yes.
Okay, so from this data 1 and 2, inlet and exit, I can calculate the work per kilogram. And this why is giving us this. Why is giving us this here? To calculate what?
Mass flow rate.
Very good. To calculate, excuse me, to calculate the mass flow. So this is what we call the sizing of the turbine. If it does not give us this here, it gives us the work per kilogram. Means what? Means that this turbine can be small turbine or it can be large turbine. Okay, because we can calculate the work per kilogram. But once he says this is 5 megawatt, means that this is a certain size of the turbine. Okay, so he sized the turbine here, similar to as giving you the mass here. So now this is a turbine. We used to have this in thermodynamics 1. Now what's the question here? The question calculate the power potential of the steam at its condition, the power at inlet condition. What does this mean? The power potential of the steam. This is the steam here, not the turbine. It is the steam
Safe.
at inlet condition. What does you want to calculate?
The reversible water.
Want to calculate
The
what?
exergy.
The exergy at state 1. Very good. The exergy at state 1 at this point here. So we want to calculate exergy at state 1. And what equation we have before? Let me just go quickly here and see the equation that we have. Okay, so this is the exergy, this point. If we put 1 here, then this will be H1, and this will be S1, this will be V1, and this will be Z1. So this is the exergy that he wants to calculate, but this is here per kilogram. Now we want to calculate, since our given the mass, then we have to calculate this in kilowatt or in megawatt. Okay, so now this is the first part. The second part, what is this? The reversible power in megawatt. What's the reversible power here?
Change in exergy.
So it is the change of exergy. So it's exergy 1 minus exergy 2. So this is exergy 1 minus exergy 2. Okay. Now this reversible work here, can I ask you how much is this? Would be more than 5 or less than 5? The reversible work.
Less than 5.
Less
يا شباب.
than. Less than.
Less than
Less
5
than.
megawatt.
More bit.
It should be more.
Oh.
This is the reversible. If this is a Carnot cycle, then we should get more work here. So this is the reversible work. You should know your answer now that it should be more than 5. And what's the difference between the reversible work and 5 megawatt? What do we call that?
Irreversible.
The irreversibility.
Reversible.
Okay.
Irreversibility.
Yes. So it's asking about the second law efficiency, which will be 5 over the reversible work. So now these are the questions here. Do you understand the problem and the question? Is it clear? Before we go to the solution. Okay.
Yes,
Right, let us go now to the solution here. First of all, because we are given the power here, and we can calculate the work per kilogram, I think it comes to our attention here that we need to calculate the mass. So we apply the energy equation. This is thermodynamics 1. M.1 H1 plus V1 squared minus M2 H2 plus V2 squared minus W out will be equal to 0. W out, the power out 5 megawatt, we are given that. H1 and H2 we can get from the tables, and V1, V2, so we can calculate the mass. So now we go to take this equation and we say that W out is equal to that. Means that M dot is equal to W out over delta H plus minus delta kinetic energy. So what is given here? Given W out, which is 5 megawatt. Remember to multiply by 1,000. Make this kilojoule per kilojoule. So this is here. So this would be 5,000 kilowatt. So in this case here, this will 5,000 kilowatt. Remember that. H1 minus H2, this we get from the table, and this will be in kilojoule per kilogram. Remember here that this, when you calculate it from the values here, you have to divide by 1,000. So now we go here, calculate delta kinetic energy, and we divide by 1,000, comes to be 6.6. So we calculate this term here. Then we go to the table, get P1 and T1, we have it here, we get the properties. This is something easy. Also at P2 and T2, get the properties. And then at P naught and T naught, because we need that H naught and S naught, we get this from the table. And here we apply here Faisal. Where is Faisal? We apply Faisal presentation, that H naught will be equal to HF at the temperature. Forget about the pressure. Alas, we take it as if you are not given the pressure. We take it at 25. H naught, you take it at 25 here. So this is what we have done with Faisal. Faisal does this for us, so we can utilize it here. All right, so we can get this from the tables. Then we go now and calculate M dot. So this is W out. over H1 minus H2 we get from the table, and delta kinetic energy we get this, so we calculate the mass flow rate. Remember here one thing, that kinetic energy, what's the difference here, H1 minus H2? Around 1,000, right? H1 minus H2 around 1,000. Kinetic energy is 6.6, so 6 out of 1,000. So it is less than 1%. And this is always the case, that kinetic energy is small. But if you forget the 1,000 to divide before in kinetic energy, you'll get this 6,600. And this will be a big mistake here. So it is better for me that this should not affect our results. Okay? So if you find that this is large, it's better for me to neglect it than to make disturbance here. So the kinetic energy can be neglected. Put this in your mind here. Kinetic energy is negligible. And as you see here, when you calculate it, it is negligible, this term compared to this term. Or otherwise, if it is, then you have 1 minute to finish your exam. Either you go back and calculate kinetic energy or drop it. Just to drop it and go ahead. This will not differ much. So instead of 5.16, if you drop that, this will be 5.18 or something. So remember here that in all our applications, thermodynamics 2, kinetic energy is neglected. It should not affect your results. Only one case when we talk about the nozzle, when we talk about the aircrafts. When we talk about the aircrafts, then this is, in this case, this will be considered. All right. I'm not going to continue this. Okay, I'll stop at this point. I leave you here to go home. What should you do at home? Solve this problem now. Okay, go home, and so you are already at home, huh? Okay. Okay, so you are at home now. Just relax, have a cup of coffee, and then solve this as a problem yourself. Calculate applying this equation here, and go also apply. Calculate the work reversible, calculate the irreversibility, and calculate that. And then I will continue this next time. I have an intention here to leave it for you, such that I want you to come next time well prepared. Hopefully you have already solved that, so we can have a better discussion. Okay, so as I announced it earlier, we'll have a quiz on Thursday, next Thursday on chapter 7. It will be from 5 points to 10 points. Okay, I'm not confident now, but if, okay, one thing I want to do as well, I'm going to give you different exams, and I'm going to change some properties. I put, for example, the mass flow rate is X, and X is equal to the 6th digit of your ID number. Okay, before I go to this, do anyone have a question in the class today? No questions. So let me say this. Okay, suppose now I want to give different exams, so I'll put symbol X, for example. Pressure is X, temperature is X, whatever, and this value will be X here will be a part of your ID number. For example, if I say this is the third ID number, third digit from the left in your ID number, so everyone can do that. If it is the 8th digit, so everyone can do that. All right? Am I understood, Shabab?
Yes.
Yeah, so I'm going to give some data are missing in the problem, but this you are going to take it from your ID number. So I can get it from the exam, so I just avoid any copy. But even if that, if I find any copy, I will, as I mentioned, we will report it to the administration. Everyone can explain to your fellow as much as you can. Please work as a team. But when it comes to exam or it comes to homework, don't show it to anybody else. So one thing that I'm going to do is, so if you copy from one else, make sure that you copy the correct answer. Huh? Okay. So thank you very much for this, and have a nice, enjoyable weekend, inshallah. جزاكم الله خير.
دكتور عندي سؤال بس.
Yes, please. I'm with